So scientific notation, it doesn't just help us sort of condense our numbers, so we're working with those really big and really small numbers in a condensed way that just doesn't take up as much room. Um, there's also some shortcuts that go along with it when you have a number written in exponential form, whether those numbers are in like a base 10 type exponential form, like scientific notation, or any number can be your base. Remember, you can write the number 36 in exponential form by writing it as 6 to the second power. So these rules that we're going to find apply to base 10 exponential form numbers and any other base exponential numbers. It could have a base of 6 or 5 or 10 or 100 or whatever. So what you want to do is kind of tinker around with these numbers. So what I've got is a table where it shows various bases, various exponents. And what we're going to do is we're going to see that if we keep those, if we do operations on these numbers while they're in exponential form, some shortcuts emerge, and we're going to be able to apply those shortcuts to numbers in scientific notation in the next investigation. So what you want to do is just pick a couple numbers in the same row. It's a really important part to this is picking a couple numbers that are in the same row and finding the product and recording your calculations with those numbers in standard form, and also show those numbers with all of them in exponential form. So for example, maybe we take 3 times 9. That's 3 times 9 equals 27. I could write this as 3 to the first power times 3 to the second power is equal to 3 to the third power. So tinker around with some of those, choose your own basis to your own exponents in the same row, and see if you see something similar to what I found there. If you do see what the connection seems to be about the input exponents and then the product exponent. Write down your ideas to see if you notice any shortcuts. Try it with a few more numbers. Try it with some numbers that don't have the same base, so that aren't necessarily in the same row. But I'm going to cut to the chase and talk about the shortcut rule that hopefully you noticed as you were tinkering with those numbers. So hopefully what you notice, if I go back up to the first one, is notice how with my example, the exponent on the product, the base 3 product, is the sum of the exponents of the two factors that are being put in the input, that multiplication problem. And you'll notice that this works for any number where it has the same base. So you'll notice that when multiplying, the exponents on the bases are added. So this could be written symbolically as if we have a base to the n power times that same base to the m power. The product is going to be that base to the power of the sum of the two exponents. And so give it a try for a few others if you haven't already. Hopefully that's what you noticed as you went down through these problems using those. But I could just show one more example. So let's say we did something like, 5 times 125 is equal to 625. So I could write that as 5 to the first power times 5 to the third power equals 5 to the fourth power. So notice that is 5 to the power of 1 plus 3. And this does not work if your numbers don't have the same base. So if I chose something like, let's say, 2 to the third power times 3 to the second power, it's really tempting to say, oh, there's a shortcut. So this must be 6 to the fifth power. So multiplying those bases, adding together the exponents. But this is 8 times 9, which is equal to 72. And 6 to the fifth power does not equal 72. Those aren't the same thing. So this is not true. So this only works if your numbers have the same base. Let's try the same thing using some division. So on this one, try the same thing. Choose two numbers that are in the same row. Find the quotient of those numbers in standard form, and then also record your calculations with the quotient in exponential form. So for example, you could take something like 256, and you could divide that by 16. And when you do that, you get 16. So I could also write this as 4 to the fourth power divided by 4 to the second power, and 16 can be written as 4 to the second power. So try a few more of those, choosing your own numbers that are in the same row. Again, write down any noticings that you have. Try to see if any pattern that you see emerging works by choosing a couple more problems, a couple more calculations to do, and see if the pattern is consistent. Try it with numbers that don't have the same base, so numbers that aren't in the same row, and then see if you can describe the shortcut rule for, typo here, this should be dividing exponential numbers. So hopefully you noticed when you were dividing that it was the inverse of what we did with our exponents when we were adding. So if you are dividing two numbers with the same base, the exponent on the quotient will be the difference between the exponents on the two numbers that you're dividing. So you subtract the exponents. We could write this symbolically. So if we have a base to an exponent, we divided by a number that's that same base to a different exponent, the quotient will be that base to the power of the difference between the exponents. So you subtract. And to show one more example of that, if we look up top, we could take something like, let's see, if I was to take, let's say, 81, so that would be 3 to the fourth power. And I divided that by 3 to the first power. I should get 3 to the 4 minus 1, which would be 3 to the third power, which would be 27. And if you do 81 and you divide by 3, indeed, you get 27. So that works. And like the other shortcut that we saw, this does not work for quotients of numbers that don't have the same base. It should be quotients. So no, it doesn't work. Try for yourself and see. So then there's some practice problems to try doing this. So on these, should be pretty quick because you don't have to deal with these numbers in their giant exponential form, or sorry, in their giant standard form. You can just deal with them in the form that they're in exponential form. So this would be 2 to the power of 3 plus 8, 2 to the 11th power. So like 2 to the 8th power is a pretty big number. I don't have to deal with that huge number if I leave it in exponential form. This would be 7 to the power of 6 minus 2, so that would be 7 to the fourth power. Again, pretty easy to do in exponential form. You don't need a calculator. And then be careful with these. With these, you can just say you cannot simplify them. So if they don't have the same base, you cannot simplify them to a single base with a single exponent. Now, one thing to be careful of is when you have a problem like this, however, be careful with your negative numbers. When you are subtracting your exponent, you're still following those negative number rules. So this one, you're doing 10 to the power of 5 plus negative 4. 5 plus negative 4 is 5 to the 1. Or sorry, 10 to the power of 1. So 5 plus negative 4 is 1. Likewise, if you're dividing, notice with this one, this would be 4 to the power of 2 minus 5. 2 minus 5 is negative 3. So that is 4 to the power of negative 3. And before wrapping up, I want to talk a little bit more just about why this works. And for the multiplication one, it's usually pretty straightforward why it works. So for example, if we were to take one of those problems, 5 to the 1 times 5 to the 6th power, it makes sense that we add our exponents. Because if you expand this and you write this as 5, 5 to the 1, then times 5 times 5 times 5 times 5 times 5 times 5. Remember, an exponent just tells you how many times that number was used as a factor. And so if we have 1 5 multiplied by 6 5s, that's 7 5s that you're multiplying together. So you're just grouping all of those factors together under one base with one exponent. And when we're dividing, let's say we were doing 7 to the 6 over 7 to the 2nd power. Expanding this also helps us explain why this works the way it does. So the top is 7 times 7 times 7. So the top has 6 sevens, the bottom has two sevens. And remember, if you may have done this when you're doing factorizations and simplifying fractions and things like that. If you have matching factors on the top and the bottom of a ratio, 7 over 7 cancels out because that's 1, that 7 and that 7, they cancel out because those are equivalent to 1. And then what you're left with is 4 sevens. So this can be written as 7 to the 4th power. So with division, it's a canceling out type process. So if you think about it, if you don't have the same base, that explains why you can't use one of these shortcuts, is because there aren't like factors to cancel out when you're dividing. There aren't like bases to combine when you're multiplying those